everybody. Good to have you back with us. We have another fantastic session. For those of you joining us for the first time, just a couple of things to help you have the best experience during your Shout online conference, which is brought to you by the Smithsonian, Microsoft Partners in Learning, and Taking It Global. We're live from the Smithsonian Environmental Research Center in Edgewater, Maryland. It's beautiful here and a beautiful start to the day. In just a moment, you'll be meeting the two gentlemen who you see in the live webcam portion of your screen. But before I introduce them, let me just say that the chat area is open throughout, so please do go ahead and use the chat on the left to say hello, to ask questions, to share resources. For those of you who are here for our first session, you know we do our best to try to get to as many of those questions as we can, so keep them coming. If you're following along on Twitter, please do share often. Shout Learning is where you can find us. It's also the hashtag. And facebook.com/shoutlearning is also a place to stay connected with Shout throughout, even beyond the conference. Pinterest is also a new place to find Shout, and you can find a growing curated collection of resources that relate to all of the Shout topics. By the way, I wanted to mention as well, many of you have already joined the Smithsonian Learning Quest site. This is a place where you can engage in an ongoing fashion with Smithsonian resources and Smithsonian experts, and also achieve some recognition and acknowledgement for the expertise that you're developing. We have a range of badges that reward contributing things like oral histories, becoming an arts advocate, or knowing what it means to be and demonstrating that you are an enviro-scientist. We have some fun badges there that really help you connect more closely with the Smithsonian, its people, and its resources. So do check out smithsonianconference.org/shout/badges, and we'll go ahead and remind you of that throughout the day. And you can join people around the world who are earning badges and becoming Smithsonian experts themselves. We are closed captioning today's event, and you will see those captions appear at the bottom of your screen. For any reason you wish to turn them off, you can set the pull-down menu from WGBH, which is our captioners, to the none or no captions position. All right. Please do use the chat and let us know a little bit about yourself if you're joining us for the first time today. And what I'd like to do, though, is I'm going to go ahead and introduce our next session, which is about the role of forests on water supply and quality. And our host is Geoffrey, or Jess Parker, who's a senior scientist and forest ecologist, and he's joined by his colleague here, an educator who is with us, Josh Falk, who is no stranger to all of you as well, and as an important part of the Shout program. Hello to both of you.
Hello.
Hi, Jonathan.
Nice to be here.
Good to have you. Forests and water.
So today we're going to spend a little time talking about the influence of forests on water, both water in a local sense, but also how vegetation influences water cycle on a global basis. So, and part of the things I'm going to talk about involve one of the forests that we have here at CERC. And the forest that you see in the picture here is an old forest at CERC. It's over 100 years old. And I want you to notice a number of things about this picture, because a number of them influence how the water influences water. First of all, you see leaves, lots of leaves in this forest. Because it's a tall forest, it has many, many layers of leaves. You can see the tree trunks. Some of them are smooth, some of them are not so smooth. What you can't see is large numbers of roots that are below the soil. And the final thing I want you to notice is that here on the ground are leaves that fell from the canopy over the last couple of years. We call that the forest floor. So anyway, this is the setting that we're going to refer to numerous times in our presentation.
And you want to start to think about why those layers are going to be important and how they affect what happens to rain as it comes down from the air, the sky.
All right then. So we'll move on to the next slide. And what we're going to do today is we're going to talk about a variety of things that are important about forests and water. First, what happens to all the precipitation that comes down and falls on a forest? And next, what can forests do about altering the fate of the water that comes in? In particular, we're going to be talking about the water that comes into the streams and the water that stays in the soil. And then finally, we're going to speculate a little bit about what happens to those flows, the quality of what forests do with water if you change the forest in a variety of ways, or if the climate changes. All right? All right, now, most of the precipitation that comes into the forests in our part of the world, we live in the eastern part of North America, comes as rain. And here's an example of rain falling onto the forest. So rain is liquid water falling in drops. But sometimes in the dormant season, when our trees don't have leaves, the precipitation comes down as snow. So it's mostly rain and snow here. But in other places in the world, and even rarely around here, we can have other forms of precipitation, such as fog or cloud water. Then there's hail, sleet, and freezing rain. And the degree to which you have those kinds of precipitation can depend on your climate. But anyway, for us, it's mostly rain and snow. Now, this complicated picture shows how the water cycle operates at the scale of the entire world over a period of about a year. And what you can see is that it's a fairly complicated diagram with lots of arrows, but I think we can simplify it in a way. First of all, what we've got is large bodies of water. Now, these bodies of water evaporate water, and it goes up into the atmosphere. And evaporation simply means a change in the state of water from liquid to a gas.
Same idea of when you boil water. It turns from liquid to gas.
Exactly. Now, when it gets up in to the cool parts of the atmosphere, that process reverses, and we call that condensation. And the water comes out of the gas phase into little tiny droplets, which, when they're in large numbers, they form clouds. Now, the clouds move a variety of ways, but in this case, let's talk about their movement over land. Now, over land, those droplets gather into even bigger droplets and they fall out. They fall down to the ground. They interact with vegetation and all kinds of structures that are on the ground, and eventually they run off by gravity back to these reservoirs of water, either lakes, seas, or the oceans. And so again, we have evaporation, movement, precipitation, and then runoff. And for a good part of our talk today, we're going to talk about what happens when precipitation hits the ground, especially if it hits vegetation like forests. All right? So just to emphasize some of these points, I want to point out that the global hydrological cycle really is a cycle. Water may change where it is or what form it's in, but it's always water. And again, the important features of that cycle are evaporation from bodies of water, movement in the atmosphere, precipitation down to the ground, runoff back to a place where the water can be evaporated again.
Yeah, and a couple things. So first off, you're talking about the water cycle and that real movement from evaporation to movement to precipitation, particularly with runoff and evaporation. You're going to hear those terms again today.
That's right.
The next two presentations, both Don Weller's and Mark Haddon's presentation, are really going to be looking at the same type of movement across a watershed, across land. And you brought up hydrological balance. That's a different word than you were using before, so what exactly does that mean?
Hydrology is the term for the study of water, the movement and the quality and all kinds of things about water. So sometimes when I say hydrology, I'll just mean the study of water.
Great.
Okay, so the second part that we want to emphasize here is that even though it's a cycle, sometimes the water gets interrupted during its movement in the cycle and gets stored.
Okay.
And they get stored in soils, sediments, and way deep in places that we call aquifers, but also in the streams, the lakes, and oceans themselves.
Right. And if actually we can even go back a slide just for a second, you can point out sort of where that aquifer would be.
So the aquifers can be deep down here in the soil or even in the rock layers. Other storage areas can be in ice in snowpack, or of course in the oceans, lakes, and streams themselves.
Yeah, and today we'll talk about soil water, which is right at the surface. So just to make sure there's a difference between that groundwater and those aquifers and what you're going to be talking about today.
That's right. For us, the soil water is the water that's very close to the surface, close enough so the trees can extract that water with their roots.
Great.
All right, on we go. Now I want to emphasize this cyclical nature once more. So again, the arrow connecting evaporation to atmospheric transport, which connects to precipitation, which connects back to runoff. And off we go. Now, here at CERC, we find that it's almost impossible to study the whole global water balance. So what we do instead is we study the water balance in our forest here.
Mm-hmm.
And what I've got here is a diagram I'm going to spend a little time walking you through, which describes the results of many years' study that we've done on how water moves through a forest at CERC. And the specific forest that I'm talking about is the one that you saw in the first slide. It's a big, mature forest with lots of leaves and lots of roots. And the important part for this presentation is that this is a deciduous forest, which means that it loses its leaves for part of the year. That's in the wintertime. And it's really not active at all. We call that dormant.
So it doesn't grow at all in that time of year, really.
Exactly. It's not doing anything. So this diagram shows a bunch of arrows that emanate from above. And basically, the arrows tell us something about what happens to the water that comes in. And I want you to think of the water in terms of the total percentage. So if we have 100 units of precipitation coming in, right, what happens to all those units? In a sense, we're going to track the life history during the forest of a bunch of drops of rain.
Right.
Okay, so 100 units of rain come in, and the rain interacts with the surface of the forest. We call that the canopy. And believe it or not, about 16% of the rain gets stuck on the top of the canopy, and it evaporates during the storm and just a little bit after. So before it even hits the ground, about 1/6 of the rain that comes into our forest is lost. It goes back to the atmosphere. Mm-hmm. Now, the rest of the rain gets down to the ground in two ways. One is it passes down along the trunks of the trees to the soil. We call that stem flow. It's not a big portion of the total water balance of the forest, but it's really important right around the bases of trees. Mm-hmm. Now, the majority of the water that gets in the forest, which we call throughfall, drips from the leaves and branches down to the soil. So these two arrows together combine and reach that layer of leaves that's sitting on top of the forest. Remember, we were calling that the litter layer or the forest floor? That's really kind of like the old canopy from the last couple of years that's sort of stuck down there on the ground. That's a protective layer for the ground. And it holds back about 4% of the water that comes in and evaporates that fairly slowly over a matter of a couple of days.
So these are one way to think about this too, is it's ways that the water is sort of slowed down as it comes through the forest canopy and through the forest as a whole.
Exactly, a whole bunch of different layers, each of which is reducing the force of the water and also the amount.
Right.
So this litter layer is kind of important. And in fact, it's the evaporation at that litter layer that gives the under part of the forest its high humidity that you may have experienced in the summertime. Anyway, so after all of those flows are subtracted from precipitation, only about 80% of the water gets into the soil. Again, the water at this level here we're calling soil water. And just so that you understand that term that describes the water getting into the soil, we call infiltration. Now that 80% of the water that finally gets into the soil doesn't stay there. In fact, 50% gets taken back up by the trees, by their roots, the deep roots of the forest trees, taken up through the trees and evaporated back to the atmosphere through these little tiny holes, which are typically on the underside of the leaves. 50%, half of all the water that comes in the forest, is taken back up by the trees and evaporated.
Right.
So when you subtract the 50% that gets evaporated from the leaves, we call that transpiration, plus the 20% that gets held up in both the canopy on the top or the canopy on the bottom, how much water eventually gets into the soil, potentially to get to the streams? Can you make a guess?
And feel free to use the chat area. We'd love to see if you're following along, and how much ultimately is continuing into the watershed and into the streams.
Mm-hmm. So what percent, like if we have those 100 drops that we were looking at, what percent makes it through?
Now remember, Josh, this is a picture of the average throughout the whole year.
Right.
It could be different in the wintertime than it is in the summer.
Right.
We're getting some answers of 30%.
That's exactly right. That shows not only can you calculate, but you also understand the importance of the forest in removing water by a variety of evaporative means.
Right.
Well, this is great.
And there's a question about, are there figures like this for different climates?
Not that I'm aware of, but it wouldn't be that hard to modify this, and we might actually try to do that.
Okay.
Before you go on, I just wanted to compliment you. My colleagues and I here were admiring this illustration, which tells such an amazing story that most people would never pause to think about, and you've captured it in this one diagram. And does this represent a fair amount of research?
Right. To get the data for this, we studied every storm that fell on the forest at Cirque for about 6 years, and it took a number of people to do that. But this diagram was actually assembled by a student of mine. So she took all that information that we had, and she organized it, and she made a really compelling, I think, picture that sort of summarizes it. So even though the diagram's pretty simple, it hides a lot of work. And later on in this presentation, I'm going to show you some of the ways that we actually got the data to make this picture.
And as I mentioned before, learning about this process is going to be really important when we learn what Don and Mark actually have to say about when that water hits the land. Where does it go?
Right. So this is Hydrology 101.
Right.
And they'll have the graduate.
They'll have 102 or maybe 202.
Okay. All right. So let's go on. So I want to emphasize again that the processes by which the forest totally reduces the amount of water that eventually gets into the soil and out into the stream are evaporation. Mm-hmm. And there's really two kinds of evaporation. First is that evaporation that happens right on the surfaces of the leaves and bark and twigs. That's passive. The plant has no control over that, and we call it interception. The other one, which is much larger, happens through the plant leaves. We call it transpiration, and it's totally under control of the plant. If the plant finds it difficult to get water, it'll slow that process down. If it's under stress, it'll slow that process down. So two different sorts of processes that control how much water actually gets out into the stream.
I'm going to take a quick aside. One of the other projects that Jess and I work on is the Smithsonian Global Tree Banding Project that allows you to measure tree growth. And you can actually measure that transpiration within a day.
That's right.
Trees are actually fatter in the morning before they lose that moisture throughout the day.
That's right. And so when the sun comes up and the tree starts to transpire water, the water is lost from the tree and it shrinks slightly. And you can actually measure that.
That's pretty cool.
All right. So we've emphasized the importance of evaporation. Now, throughout this presentation, I've been using a lot of terms that are hydrological in nature, and we've already talked about a number of them. And if you want to learn more, you can refer to the glossary of hydrology that we have a link here on this slide. But in the next couple of slides, I want you to focus on a couple of terms. One is infiltration. You've already heard that. That's the passage of water through the soil surface into the ground. Then there's runoff, which is the movement of water from the soil water, out into the stream.
And actually, runoff can be water in that soil water right on the surface as well.
It can be moving over the soil as well, right? It's just getting to the stream. And then if that water's running off too rapidly, especially over the top of the forest floor, it can wear away material. It can carry sediments and pollutants and nutrients away. So those are the terms that we're going to be using in the next few slides. But again, if this is overwhelming, feel free to consult this website. All right, so all these different components of the forest hydrological cycle need to be measured in different ways.
Right.
And rather than go through all the details on this slide, I'm actually going to show you what some of those gadgets are.
Right.
So this is a rain gauge. Very simple. It's transparent so that as the water comes in, you can actually measure the depth of the water without pouring it out. And these are available fairly inexpensively. And you can put them both inside the forest, as we have here, and you can put these also outside the forest. And when you compare the amounts in the inside forest and the outside forest gauges after a storm, the difference, usually there's much less in the forest, will tell you how much the forest intercepted and evaporated during that storm.
Right.
Remember, that's the passive part that the trees have no control over.
That was at 16% or so.
That's right, yeah, plus the 4% on the ground.
And the stem flow as well.
Right. Now, although this is not all that important to the forest hydrological cycle, I thought you might be interested to know how we actually collect the water that comes down along the trunks of the trees. So we put these plastic collars around the trees, and those are used to divert water through these pipes to this big high technology holding tank here that looks a lot like a trash can. And if you do this with every storm, you can actually calculate the total amount of water that came to the ground by that route. And this water is kind of unusual. It looks a little bit like dark tea.
Hey, Jess, quick question. Who
Shall I go back?
Yeah, just taking a look at that. Who dreams up these gadgets?
We actually dreamed up this particular approach, but other people have done similar things before. We ecologists pride ourselves in designing cheap instruments. In fact, the cheaper the better, for measuring unusual processes in nature. So this is an example of an awkward but useful approach to doing that. And that's really the point of this slide, to show you that we do things like this in order to make unusual measurements.
It also shows you that you don't need to be super complex to measure things like that.
No, that's right. And you don't need a whole lot of money. So we talked a lot about the importance of transpiration. In our forest, it involves 50% of all the water that comes in gets lost by this. Let's face it, it's kind of an invisible process. How do we actually know that it's going on? Well, if you take a very close look at the underside of a leaf, you'll see these little tiny holes. They're called stomates, which is Greek for mouth. And these are cells that can actually open and close. And they'll close when the tree wants to retain water, and they open when the tree wants to evaporate water. These are very, very small, and the leaf has an awful lot of them. In fact, we figure that an average leaf, say about the size of your hand, can have about 1 million of these little holes. And they're all under the control of the tree. So they have a substantial amount of total area, which can control how much water goes in and out. So those are the stomates.
I think we have a little poll there.
Oh, so yeah, we were. So what we wanted to know is, through these holes, how much water do you think an average tree can transpire during the course of, let's say, a warm midsummer day?
How much will it lose?
That's right. How much water that was in the soil near the surface is now going into the atmosphere.
You know, what's really neat about that stomate picture, too, is you think about trees being passive and not being really in control of their environment. It's really neat to think about the fact that they actually do control a little bit about their destiny, how much water they're keeping in.
That's right. In a sense, trees are like straws connecting the ground, the water in the ground, to the water in the air, and they have a little valve at the top, and the valves are the stomates. So it looked like we're getting answers that are pretty much in the 10 to 20 gallon range. In fact, a medium to large sized tree in our forest can transpire 20 to 100 gallons a day. And even the larger trees can do even more than that. And you can imagine a redwood tree in the coasts of California could do a whole lot more than that every day. All right. So
that's also actually another reason why you see those forests are so much more humid, is that the understory trees are doing the same thing.
They are.
And the plants are doing the same thing. And
that's That's right. It's going on.
Smaller plants.
In fact, if the tree didn't transpire, it wouldn't be growing. Right. Transpiration is important because you need water to balance the photosynthesis equation. You need water to grow the cells. And also, you need water to cool down the leaves to keep them from overheating. All right. So how do we measure this, this transpiration process? Well, it's really hard to do. But in recent years, a technology called the Sap Flow Gauge has been developed. And basically the approach is to measure the velocity at which water moves up in the tree. Now you can't see that water, but what you can do is you can tag it. So this part of the sap flow meter actually heats up the water inside of the trunk right about here. And as that water moves up, these thermometers here can measure the temperature change as the water moves up. So in a sense, you can figure out how long it took the water from here to get there, and that gives you an indication of the velocity. And from that, you can calculate the rate at which the water moved up in that tree. So that's for this tree, and then you can calculate how much it moves for all the trees.
I can't decide which gadget I think is cooler, this one or the octopus trash can collector.
This one's more expensive.
This one's a lot more expensive, right?
Then I like the other one.
And this one also requires sort of a mini computer that we call a data logger to keep track of the numbers as they come in, because this velocity will change during the course of the day. In the morning, it'll be nearly zero, and as the day proceeds and as we have more and more sunlight, the velocity will go higher. And then, of course, as sunset approaches, the velocity will reduce to zero again. Anyway, so these are some examples of the different kinds of technologies that we use to measure the different parts of the water cycle in the forest. Oh, actually, here's the last one that I forgot. When the water finally moves from the soil water into the stream, we'd like to know how much is moving out of the streams. And this is an instrument called a stream gauging station, which actually sits about 200 feet from the very forest that we were studying so intentionally. So the water moving out of this stream here is water that originated in precipitation falling on our forest, made it through all those layers that you spoke of, into the soil, and then from the soil back into the stream.
And actually what's really neat about this picture is the scientist in the picture is the scientist that you guys heard speak, I guess, 2 months ago, Tom Jordan.
Right.
And it's a real good example of what we do here at CERC as well, and that we have a bunch of labs that work on global issues, but use CERC as a sort of mini lab for larger issues, and work together on solving complex issues together.
In fact, this scientist, Tom Jordan, works very closely with Don Weller, who you'll hear about, I think, in the very next presentation. Anyway, so this is a way of measuring the flow of water out of the forest. So this is the fate, in a sense, in our ecosystem of the water that came in as rainfall to the forest.
So in theory, that's the 30%.
That's the 30%, right? And that's averaged over the year.
Correct.
Notice that the forest in the background in this picture is nearly leafless, okay? Whereas in the very first photograph I showed you, it was fully leafed. Now, what happens to the water that comes out of that stream in different seasons of the year? And here's some data that we've got from that very same stream flow gauge. And let me walk you through this, okay? Down along this axis, we have time, 3 separate years. And each of these letters here gives the month. So that's June and July, all the way through to January. And on this axis here, we have the total amount of water in millimeters per month that came through that instrument every month. And so the tall bars are months when we had a lot of water coming, and the small bars are the months with very little. And what I want you to notice is that not all these bars are the same height. Right? So that means that there's something going on in different seasons than in other seasons. And in fact, what I notice is that during the summertime, these are June, July, August, and September, there is very little water moving out of that instrument. Again, here's another summer, and here's yet another summer over here. Whereas in the winter and spring, there's a lot of water moving out of that instrument. And here's another winter and spring. In fact, this pattern goes on year after year. And so I'm wondering, does anyone have an idea why there is so little water here? But before we do that, let's ask this question about when, in certain times of day and year, trees do most of their transpiring.
Okay, so we've got our poll first.
I guess we should have a look at this poll. It looks to me like we're not having many takers for anything except summer night, summer day.
Not a song.
Hum a few bars. I don't know. It looks to me, Josh, that a lot of people are opting for summertime in the daytime, and I think that's about right. You need sunlight energy, and you need the leaves to be active.
Correct.
And so both of those conditions are met in the summertime in the day.
There's probably a little residual at night, but
there probably is a little bit, yes, especially when you have the intercepted evaporation. But here we're talking mostly about the transpiration.
And so back to this picture,
yeah.
This chart here. Jess had also asked, why do we think there's more stream flow in those spring and winter months? And before you answer, because we do want some answers in the chat bar, keep in mind that here at CERC, our rainfall is about the same from month to month. It doesn't change. So that is not the reason why there's more. All right, so let's give people a second to think, to answer.
We had one response, perhaps the trees aren't taking up water yet. Let's see what other people have to say. Go ahead and share with us. What do you think accounts for the difference during those particular months? You can see them again on the chart. We've got the arrow pointing to them, right?
Mm-hmm. So the arrow is currently pointing towards the summer and early fall months, and what we typically see is very little rain. As a matter of fact, it's not uncommon for the streams around here, the small streams, to run totally dry in those periods of the year, even though there's plenty of rain coming down. And so we're getting a few answers in.
One option is less use by plants allows more runoff and water penetration. Kendra says because of more sunlight. Maybe just before you explained the consistency in rainfall, Anna had speculated maybe it was related to there being no rainfall. There's a lot of snow precipitation in the winter, says Fiona. How are people doing? Anyone close?
I think some of those answers are related, and I think some of them are spot on. We think the reason that the stream flow around here goes to nothing in the summertime is because the trees are extracting it. So that's the time of year when the percentage of evaporation is probably higher than the average because the leaves are active and the sun is up. Whereas in the wintertime, when there are no leaves, the forest is dormant, the percentage of evaporation is probably less than average. So that was good. So here's another example of not only how does the forest reduce the total amount of precipitation by a variety of, the amount of precipitation it gets to the streams, but it also changes the timing of it in the year. Okay.
So it controls it.
It controls it, right. All right, let's, what we've done in discussing the well-studied forest here at CERC is to show how the forest, largely through the many layers that it has, but also because of the different processes of evaporation, it can control the amount of streamfall. And also we've shown by looking throughout the year that it can control the timing of the stream flow. In fact, it can control the timing of stream flow on a much shorter time scale too. Rather than have all the water flush off in a few hours, it can change that so it takes several days. And I think the next presentation is really going to focus a little bit on that. Don. And because it can reduce the force of the water, it can also reduce how much that water is holding. And that would include nutrients, pollutants, but also sediments, little particles. And of course, all that contributes to what we call the quality of the stream water. And again, this will be dealt with in quite a bit more detail in the next presentation.
Yeah, and really be thinking about if the water doesn't have as much stuff in it and is going slower, what effect will that have once that runoff hits other bodies of water? Is that important? Is that what we want? That's what we're interested in.
And if I recall from the last presentation, the nutrients that are and the sediments that are held in those waters can have a substantial effect on what lives in the water and how fast it grows, and actually, what kind of creatures those are. All right. So now I'd like to talk a little bit about what happens if we manipulate the forest. What happens if we take the forest and we replace it with another kind of vegetation? Here I've got an example of changing a forest into a different kind of vegetation. Very short vegetation with not much leaf area and with fairly shallow roots. This is an example of a lawn, which is very common in our part of eastern North America. What do you think a vegetation situation like this does to the water cycle compared to a forest?
We put that question on the side for folks. What happens if we replace a forest with shorter vegetation like a lawn or a field? What do you think happens?
So in particular, what happens to the water is what we're asking.
That's right. So first of all, let's just talk about the total amount of water. And remember, a lawn is different from a forest in that not only is it shorter, but it has fewer layers of leaves, and also it has less roots.
Right.
And because the roots are fewer and more concentrated near the top, they're probably not as able to remove water for transpiration as a forest is.
Right, and when you mean fewer leaves, you mean in two spots. One is that canopy,
right,
and the other is that leaf litter.
That's right.
All right, so I've got.
Let's see.
The sixth graders in Berks County, Pennsylvania, say that it gets eroded faster. More runoff, less infiltration, depending on the rainfall amount Anna offers?
I think you're right, because this situation provides less evaporation, both the passive kind that we spoke of, that happens just on the leaf surface, and the active kind that happens under the control of the plant. More of that water is getting into the ground, and therefore more of that water can get into the streams. Now, the presence of the grass can slow that process down, but maybe not as well as a forest can.
Well, and when we're talking about slowing down too, think about during a big rain event. I know I've walked by a lawn and seen huge puddles or rain sheeting off and not getting slowed down. And so that in that case, it's sort of being wasted on the grass. It's just running right off.
That's right. So it turns out that the soil, remember this process we talked about, infiltration, that's the movement of water into the soil. Some soils have a certain capacity. They can take so much water, but no more. So if you exceed the amount of precipitation coming into the soil, it can't go in. And so where does it go? It either gets stuck on the top of the forest, or it runs off on little mini rivers that collect into streams and stuff. So, okay, this is an example of one thing that you can do if you have a forest and you decide to change it. Let's look at another example. Here's another common example in our part of the world where we've replaced vegetation with what we call an impervious surface. Now, an impervious means it won't let water pass. And this is a real typical example. This is a parking lot.
Yeah, think about what happens when you pour water on a table.
That's right.
It doesn't soak in.
It doesn't soak in at all. So, Josh, what do you think happens to the rainfall that falls on this asphalt surface, or even a concrete surface? What happens to it?
Well, in most places, when it rains on a parking lot, it goes into a storm drain, and that storm drain goes straight with no filtration, no infiltration, straight into another body of water. So it picks up speed, sometimes picks up temperature, and then picks up all the stuff that's in the parking lot.
Right, so it doesn't really have much chance to interact with the ecosystem. It just bypasses it.
And in some cases, almost zero until it hits the water.
That's right. So now, of course, we need this kind of surface in our culture, but we don't necessarily need all of our surfaces to be impervious. And so there's actually a movement to try and find new sorts of materials that will actually allow the water to penetrate into the soil somewhat.
Yeah, and actually, looking at this picture in particular, what a lot of people are doing is You see these islands here? They're allowing the water to drain into those and putting trees in those islands. And those trees allow it to slowly infiltrate into that soil water and groundwater rather than going straight to a storm drain.
So what the intent of those modifications is to allow the water to interact with as much of the soil and the vegetation, really the ecosystem, as you can, rather than bypassing it. Well, that's good. Let's talk now about an extreme example of a modification of a forest. This is a forest that has been cleared of trees in the western United States. Sometimes clearing of trees is necessary to get lumber, to get wood. But in this particular case, you can see that the slopes are very, very steep. All the trees have been removed, and it looks like there's very little forest floor here as well. What do you think the influence of this change in vegetation is on the water cycle? Can you suggest some consequences of this? That would be a question, I think, for our chat.
Yeah. So and how is this different than what happens when it falls on a normal forest or falls in a parking lot or a
lawn?
Or a lawn. Or is it the same as some of them?
Maybe. Anyway, we don't want our discussion of how modifying forests changes the water supply to end here. Right. We're hoping that you and your class, or you in your discussions, think about some of these things, and as you travel around and see different situations, you might consider how those modifications can change this important part of our environment.
It looks like Anna and Marlene are right on with their answers there.
Oh yeah. There could be terrible erosion. And why is there erosion? It's because there's very little interaction with the precipitation with the system. There's very little opportunity for the water to penetrate. Right. There's nothing to arrest the force and the velocity of the rain. Mm-hmm. And so you can have the removal of the little layer, and you can have the removal of the topsoil.
And actually, as that topsoil starts to move to get removed, the floor gets more and more impacted and soaks up even less and less moisture as well.
So it's sort of a self-accelerating process. Mm-hmm. So now these days, when we cut forests in this way, we tend to try to leave living green vegetation along inside the streams. And I think Amy was talking earlier about riparian vegetation. That's vegetation along the streams. Mm-hmm. Well, nowadays, we try very hard to keep that vegetation there so it can form sort of a buffer and allow or force at least part of the precipitation to interact with the ecosystem. Right. And I think this is another one of those topics that the subsequent speaker will be talking about. Right. Okay, so we've showed a number of ways in which forests can be modified, and we've talked a little bit about what those might mean for the water cycle. And so to sort of summarize this, and again, rather than end the discussion here, we're hoping this could be a starting place for what you talk about in your class. We were posing the final question: what happens to our water cycle when you change forests? Sometimes that's called management. You can replace them, you can modify them in a variety of ways. Or what happens if the climate changes? And by this I mean more or less rainfall, more or less sunshine, hotter temperatures, cooler temperatures. So we've talked a little bit about what happens if you replace a forest with a lawn or a parking lot. We've talked a little bit about what happens if you totally remove the forest. We haven't talked so much about the removal of the litter layer, but as you know, the litter layer in the forest is important for a couple reasons. One is it slows down the impact velocity of the raindrops, and also it does some evaporation, but also it forms a sort of a protective barrier over the top of the forest. And what you might do in your discussions is to think a little bit about what happens if the future involves more storms, bigger storms, or let's suppose we go into a droughty situation where you have fewer storms or smaller ones.
Yeah, trees in certain areas are adapted for a certain climate, and if that weather pattern changes, how are they going to adapt? Can they adapt to that?
So there's an awful lot of questions that we can start trying to discuss here.
Mm-hmm.
And all right, so let me just summarize here by talking about the kinds of things that we've covered.
Right.
First of all, we talked about the various parts of the hydrological cycle. And I kind of dazzled you with terminology, I know, but it turns out that some of those terms are kind of important when you're trying to break apart the complexity of the hydrological cycle.
Mm-hmm.
We looked at it at a global basis, and we discovered that on a global basis, it's clearly a cycle.
Mm-hmm.
Water is moved from place to place, changes its form, but it's always water.
Mm-hmm.
It's sort of the classical recycling.
Mm-hmm.
Then we looked in some detail at how the hydrological balance is manifest in a forest, the kind that we're very familiar with here. And we looked at a variety of things that forests can do. They change the amount of water that comes into it, and I guess the operative number in our case was only 30% of the water that comes into our forest actually makes it out into the stream.
Mm-hmm.
We talked a little bit about the timing, both in the season and during a rainstorm. And we talked a little bit about the quality of the water and its capacity to erode surfaces. Again, there's going to be more about that in the next talk. And then we also talked a little bit about how changing the forest can affect all of those things.
Well, and affect how humans interact with the land too.
Sure.
If there's more velocity, more water coming down, how does that affect your local stream, your street, etc.?
Right. So a lot of things we've talked about here are going to be followed on and amplified in the next couple of talks. But I'm hoping that you'll use some of the points that we've brought up here today as a framework, possibly, for your discussions about the importance of forests, in fact, of vegetation in general, on the water balance of the world and of your locality.
Thank you both very much. We would love to take some of your questions. We have a couple of moments to do that. We had a comment from somebody joining us from North Carolina who said they lost lots of trees last year with Hurricane Irene. In terms of arguably natural processes that that affect the amount of trees and therefore also the water flow within a system, when you think about the cycle, do you include hurricanes and natural processes in that?
You know, in a sense, the influence of hurricanes and events like that, we ecologists call those disturbances. They're sort of built into our averages because although they're unpredictable, they're inevitable. Eventually there will be a storm. There will be some process that kills a number of trees. But what we've discovered, especially in the forests around here, is they're quite resilient. They respond nicely, and so both the structure of the forest and their ability to control water flows is usually recovered fairly rapidly. So it's an ugly thing to see when you have a hurricane destroy half your forest, but its effects are probably fairly short term.
And I guess the sort of the next look at that is that if there were several hurricanes in a row, that's something that you don't plan on. You know, you plan on one or two a year maybe in certain areas.
Or if you're smack in the middle of the front of it, yeah.
Right. And so that is something that's a little harder to quantify, and then honestly it's something you study to see how the ecosystem reacts to.
Indeed we do.
One of the things that amazes me about hearing you share what you have about the hydrological cycle with us today is it can seem so large and unstudyable, if you will. How do you go about figuring these things out? And I liked how you gave us a little window into some of the processes you use, and many of them are very accessible. What kind of advice or guidance do you have in terms of asking questions, and then what can people, what kind of advice do you have on trying to use approaches like you have to try to answer some of these questions? What are some good questions you think that some of our learners might want to pursue themselves?
Well, let's see. Let me answer that in two ways. Okay, first of all, one of the nice things about the science business is that it's actually possible to ask a question about a big process and have a hope of answering it. And so some of those gadgets that I showed in earlier slides are a way of doing that. And this is particularly difficult in the case of the water cycle because a lot of what is going on, even though it's big and important, is invisible. I don't know about you, but I can't see water vapor. And I can't see the water moving up inside the tree. You have to believe that it's going on. But there are ways to see that. And still on that subject, let me point out that if you really want to be sure that transpiration is going on, go and take a plastic bag and put it around a twig with living leaves in it for a day. And come back after a day and look inside the bag. You'll see some water in there. And where'd that water come from? So here's a simple way of convincing yourself that this transpiration thing is real, not just something that I've told you or that you might have read in a textbook. So even though it's a big process, parts of it are accessible, and all you have to do is put a little imagination to it, not necessarily a lot of money, and you can actually tease out some of those things.
We have just a moment left. I wanted to sneak in quick answers to two more questions that have come in. One is, are there any trees that affect the water cycle more than others?
There are some trees that are actually greedy when it comes to taking out water. And in places where water is scarce, such as in the desert southwest, there are some trees, some of them are invasive species that Amy didn't mention, that actually live by the sides of streams in desert areas, and they really take up a lot of water. Now that's nice for them because they grow well and their progeny do well, but it's not so nice for their neighbors. So I wouldn't say that's a globally important effect, but for right there, it can be very important. So there's an example of how certain kinds of species can do things that are different from the average.
Great, thank you. And the last question, and stay tuned because we have a lot more ahead, is are flash floods caused by the destruction of these forests, or are there other causes?
So I don't know if I can speak to all flash floods, but in general, a flash flood is when an unusual amount of water comes through a stream at one time. And this can have a variety of causes. And I think Dr. Weller is going to speak a little bit about what can happen in certain cases when a lot of water comes through a stream measuring station. But what we often find is that those flashy conditions happen when the system delivering water to a stream is relatively impervious. So it's not interacting, the water coming down is not interacting with the system. There's no way to slow it down, and away it goes into the stream.
Yeah, or if there's just more water than it can handle.
Exactly. There are occasions when you have huge amounts of rain that no ecosystem can really deal with.
Right, and I think the answer to Adam's question is sometimes.
Sometimes, yeah.
Sometimes.
Or, as an ecologist would say, it depends.
Well, one thing that is certain is that this was a very meaningful, important session, and we thank you for so clearly walking us through what could otherwise feel like it is a very complex topic, but you both made it very accessible to us, and I know I learned a tremendous amount. I'm sure I speak for everyone here, so please join me in using the chat on the left and sharing some feedback about your experience here today and your gratitude for our presenters, Jess and Josh. I also want to encourage you, if this is the last of the sessions you'll be able to attend with us live today, please do click the evaluation link at the top left corner and give us some feedback. If you'll be joining us for one or two of the other sessions, and we hope you will be, feel free to complete that evaluation at the end of your experience with us today. I agree, Fiona, this was a very cool session, so thank you for your feedback from Lake Bluff and from and to everyone who are sending us in their feedback as well. Don't forget that our next session, which will start in just about 5 minutes, we'll ask the question about how we can stop polluting the water with elements that are essential to our lives. How do we manage this dilemma of needing things but knowing that they're causing problems at the same time? What can we do? So our host for that session will be Don Weller. He's a senior scientist here in the Ecological Modeling Lab at CERC, and he'll be our host. Also, don't forget, you can follow us on Twitter and on Facebook. Shout Learning is the place to look. And I did want to make one more quick plug to have you consider joining us and digging deeper into the topics you're learning about during Shout.